Hi everyone, this is Mrs. GA, and today we're going to be working with complex zeros and the fundamental theorem of algebra. So the fundamental theorem of algebra essentially states that every polynomial with complex coefficients has at least one complex zero. So it's important to note here that real numbers can be considered complex zeros. It's just the imaginary portion of the complex number has a coefficient of 0. So it's essentially saying every polynomial has at least one zero, whether it's real or imaginary. Okay, so let's start with example 1 together. So here we're going to find all zeros and we're going to do a complete factorization of this polynomial. So for something like this, we always check to see if we can factor first. And in this case, let's try to factor by grouping. So for the first two terms, I notice there's a GCF of x squared, so x minus 3. And then I could say plus 1 times x minus 3. So here I get x squared plus 1 times x minus 3. So with this, I can find the rest of the zeros. So I can do zero product property from here. I can set this factor equal to 0 and solve. So I see here that I have x equals the plus or minus square root of -1, which hopefully we remember is I. And then here I have x equals 3. So my three answers are 3, positive I, and negative I. So two of them are imaginary and one of them is real. Now to do a complete factorization, we can write this in this form. So x minus 3 stays the same, and we can actually write this as x plus I and x minus I. So treat your i's as if they were any real zero. So again, these are our zeros, and then we call this a complete factorization of the polynomial. Okay, let's try another one together. So here you might look and you say, I can't factor this, so I need to do the rational root theorem. So I need to list out my p's and my q's, so I have a list of potential options. Just remember, p's are all of the factors of your constant, q's are all of the factors of your lead coefficient. So we do all possible combinations of p over q, so plus or minus 1 over 1, 2 over 1, or 4 over 1. So let's say I try -2 first, and I'm going to do a little synthetic division. So I have 1x cubed plus 0x squared minus 2x plus 4. Let's check. And it happens to work. So what I have remaining, so I have p of x equals x plus 2. So remember, if my 0 is -2, then my factor is positive 2. And then what I have left is x squared minus 2x plus 2. So this is not factorable, but it is a quadratic, so we should be able to solve. So I'm going to do a little quadratic formula here. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. So I have 2 plus or minus. So here I have 4 minus 8, so it becomes -4 all over 2. And then you'll see here that I end up with an imaginary number here. So this simplifies to x equals, go back to blue, x equals 2 plus or minus 2i all over 2, which simplifies to 1 plus or minus I. So I can see that my three answers are x equals -2, 1 plus I, a complex number, and then 1 minus I. Or if you would like to write it as 1 plus or minus I, that is fine as well. Now to do the complete factorization here, we have to be careful. So remember, our general process is x minus our 0. So x minus -2 becomes x plus 2. And then we're going to do x minus, and then in parentheses, 1 plus I. And x minus parentheses 1 minus I. Don't forget that we're subtracting this entire 0. and then let's just distribute that out. So I have x plus 2 times x minus 1 minus I times x minus 1 plus I. So this is the complete factorization of my polynomial. Okay, so now we're going to talk about zeros and their multiplicities. So we've talked about when we are graphing what happens on a graph when we have a repeated factor. So if a factor appears k times in the factorization of p of x, we say that this zero has a multiplicity of k, or however many times it's repeated. So repeated we call multiplicity. So the zeros theorem says that for every polynomial with a degree of n is greater than or equal to 1, so it has to have at least a degree of 1, the polynomial has exactly n zeros. So the number of zeros should match the degree. However, this could be real or complex and imaginary zeros. And then we have to assume that our multiplicities are counted. So if we know that we have a multiplicity of 3, we count that 0 3 times. I also want to talk really briefly about what's called the conjugate zeros theorem, which may help you to find zeros that you're missing. The conjugate zero theorem essentially says that all complex zeros come in pairs. So for example, if you have 2 plus I, you're always going to have 2 minus I. So that will help you to make sure that you have all of your zeros. Okay, so let's see if we can find all the zeros and do a complete factorization of this polynomial. 3x to the 5th plus 24x cubed plus 48x. So I'm going to start by factoring. So this one does have a greatest common factor of 3x. So I have 3x times x to the 4th plus 8x squared plus 16. So then if I factor this, imagine this said x squared plus 8x plus 16. It'd be pretty easy to see that this is x plus 4 squared. So we're going to kind of use the same general idea, but instead of an x here, we're going to have x squared. So it's x squared plus 4 squared. And this will work as long as this exponent is double this exponent, and this is just a constant. So here we have our factors allowing us to find our zeros. So if I do zero product property, I set 3x equal to 0, and I set x squared plus 4 equal to 0, noting that it has a multiplicity of 2. So I can solve, and I get x equals 0 here. I'll use the square root method here. So I get x equals plus or minus 2i. Because if I take the square root of -4, I get plus or minus 2i. So both of these, again, both have a multiplicity of 2. And the reason why is because our factor was squared. So let's see if we can list out our zeros to see if it matches our degree. So I have 0, and then I have positive 2i, and then negative 2i. And remember, this one is counted twice, and this one is counted twice. So I have 1, 2, 3, 4, 5, which matches my degree. So we have all 5 of our answers. 4 of them are imaginary, and then 1 of them is real. So to do a complete factorization of this, we would do 3x times x minus 2i squared times x plus 2i squared. And this is, again, what's called the complete factorization. So again, that property that we talked about, we can use it to make sure that we have all of our answers. You just have to make sure to count the multiplicities to make when you're adding up the zeros that you list. Okay, so now we're going to try something a little different. We're actually going to go backwards from what we've been doing. So we're going to see if we can actually create the polynomial given the degree, zeros, and maybe some information about the polynomial. So here it says the degree is 4, and the zeros are x equals I I'm going to leave a little space for a reason I'll talk about in a second, 2 and negative 2. So maybe you're saying, hey, wait a minute. It says the degree is 4, but they only tell us 3 of our zeros. So here we need to know that complex conjugate theorem, which says that complex zeros always come in pairs. So even though I didn't say this in the given, it's implied that negative I is also a 0. So if I'm told one of my complex zeros, you should be able to know that the other one exists, and it's always going to be the complex conjugate. So now we're going to set up the polynomial. And since it tells us that P of 3 equals 25, we can use that information to adjust for any like vertical stretch or shrink. So I'm going to place an A out front, and we're going to solve for this A value in a moment. And then I'm going to turn my zeros into factors. So I have x minus I, x plus I, x minus 2, and x plus 2. So I'm going to start multiplying this out. So I have A. My tip to you is always multiply your complex factors together and then your real factors together. So this becomes x squared. And then here I have minus I squared, which remember becomes plus 1. Remember, I squared is negative 1. And then if I multiply out my two real binomials, I get x squared minus 4. And then these I can multiply together. So I have x to the 4th. And then here I have minus 4x squared plus 1x squared. So minus 3x squared and then minus 4. So now we can use that last piece of information we were given, that P of 3 equals 25. So essentially they're telling us an xy value that works for our polynomial. They're telling us that the coordinate 3, 25 exists. So that means that I can replace all of my x's with 3, and I can replace my y with 25, and then I can solve for my a value. So again, I'm going to replace y with 25. Then I have a times 3 to the 4th minus 3 times 3 squared minus 4. So again, I went in and I replaced all of my x values with 3, and I replaced my y value with 25, allowing me to solve for a. So if you multiply this out, you get 50 in here. So I have 25 equals 50a, which means my a value is 1/2. So now I can go back and place that right here into my polynomial. So P of x equals 1/2 times x to the 4th minus 3x squared minus 4. And I'll just distribute that in, so I have a nice polynomial. So 1/2 x to the 4th minus 3/2 x squared minus 2. And here is my polynomial. So this polynomial, again, has a degree of 4, and it has the zeros I, negative I, 2, negative 2, and it goes through the coordinate 3, 25. Okay, let's try another one together. So this one says find a polynomial p of x with a degree of 4 that has zeros at negative 2 and 0, where negative 2 is a 0 with a multiplicity of 3. And notice this time they don't give us a coordinate it goes through, which means we can pick whatever a value we want. So let's set up our factors. So we have p of x equals, so we have x plus 2, because the 0 is negative 2. And then since we have another 0 at 0, I have x. And since it says negative 2 has a multiplicity of 3, I'm going to cube it. So now I need to multiply this out. So p of x equals x times. So if you multiply this out, remember you can't just distribute the exponent. You need to do x plus 2 times x plus 2 times x plus 2. You get x cubed plus 6x squared plus 12x plus 8, and then we're going to distribute in the x. So x to the 4th plus 6x cubed plus 12x squared plus 8x. And again here, we could set an a value out front, but since they didn't give us a specific point it goes through, we can pick whatever a value we want. So I'm always going to pick a equals 1. So we can keep our polynomial exactly like this. And there you have it. Okay, so go ahead and pause the video and see if you can give this one a try. And be careful because you might notice that I'm only telling you 2 of the zeros, but there should be 3. So see if you can find that missing 0. Okay, let's check. So hopefully you notice that the missing 0, so we have a 0 at 3, 2i, and negative 2i. Remember, the complex conjugate theorem says that our complex zeros will always come in pairs. So I have my 3 zeros, my 3 factors, a little out of order, but it's okay. And then I just multiply it out and simplify it. So again, if they don't tell you a specific coordinate it goes through, we can pick whatever a value we want for our polynomial, and the easiest one to pick is always 1. Okay, so for this next one, we want to find a polynomial that has a degree of 2 and a 0 at 1 plus I root 2. So again here, hopefully you notice that something's not quite right because they only tell us one of our zeros, 1 plus I root 2, but it has a degree of 2. So according to the complex conjugate theorem, our other 0 will be 1 minus I root 2. So now we can make our factors. So here, we need to be careful. Remember, the way you make a factor is by subtracting your entire x value. So I'm going to say x minus, and then I'm going to group 1 plus I root 2. And then here I'm going to say x minus, and I'm going to group my other 0, 1 minus I root 2. So in multiplying this out, I have a little tip that's going to make this much, much easier for you. So I am going to distribute the negatives within my individual factors, but then I'm going to do a little grouping trick that will make your life way, way easier. So when I multiply this out, I get x minus 1 minus I root 2, and I'm going to group x minus 1 together and leave the imaginary 1 on the outside. I still distributed, but I'm going to group these two together. And I'm going to do the same here. X minus 1 plus I root 2, but I'm going to group this together as well. So now, when I go to FOIL this out, I'm going to treat this like a binomial times a binomial. I'm going to do this entire term times this entire term. So that gives me p of x equals, so I'm going to say x minus 1 squared. And then if I take this and I multiply it here, I notice that it will cancel out with my next step of FOIL. So this would give me I root 2 times x minus 1, and then I have negative I root 2 times x minus 1. So again, this multiplication cancels out with this one. And then all I have to do next is multiply my last two terms together. So this becomes minus I squared times 2, because square root of 2 times square root of 2 is 2. Now let's simplify what we have and expand out a little more. Remember, I squared becomes negative 1, and I am going to multiply out this binomial at the beginning. So it becomes x squared minus 2x plus 1, and then this becomes plus 2. So my final answer, if I combine my constants, is x squared minus 2x plus 3. So again, grouping x minus 1 here and here, and noticing that it's the same thing in both parts, it can save you a lot of time, because then we're using x minus 1 as a single term in FOIL. So I would really recommend doing this when you're multiplying out this polynomial. All right, so here, see if you can pause the video and give this one a try, and please try to use that little grouping trick I just showed you to multiply it out. Okay, so again, we were only told 2 of our zeros. We were told that x equals negative 3 and 1 plus I. But we should know that we also have the 0, 1 minus I because of the complex conjugate theorem. So this, so I have 3 factors, x plus 3, x minus 1 plus I, and x minus 1 minus I. So again, here's that little grouping trick that I just showed you guys. We are going to distribute the negatives, but then I'm going to regroup x minus 1 and treat it as a single term. So when I FOIL it out, it becomes x minus 1 squared. This cancels out with this, and I have minus I squared. So then you're just simplifying and then multiplying this binomial to this trinomial to get this as your final answer. Okay, so now we're going to try to use everything that we've been learning and talking about to see if we can find all of the zeros, both real and complex, of this polynomial. So again, we need a starting place, so I'm going to be using the rational root theorem to give me a list of values to try. So if I do my p-values, I have 1 plus or minus 1, 2, or 4. For my q-values, I have plus or minus 1 and 3. So all of my possible combinations would be plus or minus 1 over 1, 2 over 1, 4 over 1, 1 over 3, 2 over 3, and 4 over 3. So let's try using 2 first. Let's try 2, just because I have a hunch that that one will work. So I have 3, negative 2, negative 1, negative 12, and negative 4. Let's see if we get a remainder of 0. So I have 6, 4, 8, 7, 14, 2, 4, and 0. So it worked. And then let's see what we have left. So right now we have x minus 2 times 3x cubed plus 4x squared plus 7x plus 2. So you can see that what we have left is a polynomial that can't be factored. So let's restart the rational root theorem, and I'm going to relist my p over q's to try. So I know that it's 2 over 1, plus or minus 2 over 1, 1 over 1, and then I can do both of those over 3. So 2 over 3 and 1 over 3. And just because I have a hunch that it might work, let's try negative 1/3. So don't be afraid to try the fractions. I'm going to list out my coefficients and see if I get a remainder of 0. Okay, so 3, and then this gives me negative 1, and then I add 3, and then negative 1, 6, and then I have negative 2, 0. So I see that it worked. So I have p of x equals, so I had the factor x minus 2. Now I have the factor x plus 1/3, and my remaining polynomial would be 3x squared plus 3x plus 6. So from this, we can factor out a GCF of 3. So let's reduce that down a little bit. So 3 times x minus 2 times x plus 1/3 times x squared plus x plus 2. And now I have a quadratic equation. So even though this quadratic equation is not factorable, we know that we can solve using the quadratic formula. So let's do that on the side. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So x equals negative 1 plus or minus. So here we have 1 minus 8. So the square root of negative 7, telling us that we're going to get two imaginary numbers. And so our last two solutions are negative 1 plus or minus I root 7 all over 2. So that's two of our answers. And then from up here, we also had positive 2 and then negative 1/3. So you can see here that we have a polynomial that has a degree of 4, and I do have 4 answers. I have 2 real ones and 2 imaginary ones. So hopefully you can see how this kind of ties together everything we've been working on. All right, this is the last example. Please give this one a try, and it might take you a little bit of time, but it's really important that you work through the entire problem. Okay, so go ahead and check your work here. So on this one, start by listing out your potential values, and the first one I found that worked was +5, leaving me with this polynomial. So from here, I'm going to redo my rational root theorem, and the next one I found that worked was -1/2. So that leaves me with these two factors in this quadratic, which I know that I can solve, so I'll factor out a 2 first, and then I will finish solving with the quadratic formula. So again, my degree is 4, and my answers confirm that because I have 2 real solutions and 2 complex solutions, giving me a total of 4 solutions. Okay, that is all for today's video. Thank you so much for watching.